the concept of absolute value or magnitude, sometimes you hear it called, because when we talk about numbers and we're not interested in the actual sign in the front, but just the size of the number. The formal definition of absolute value is this. It's the absolute value of A is A if A is greater than or equal to 0, but it's negative A if A is less than 0. So then the negative times the negative becomes a positive. So that's the formal definition. The way we think about it, if we think about our number line, it's simply representing the distance from 0. As I was saying, it's magnitude only. The direction, whether it's positive or negative, really we're not worried about. So, I mean, very basic example there. Absolute value of minus 5. Well, it's simply, it's 5 units away from the origin, so the answer's 5. Absolute values are just grouping symbols, like any other grouping symbol. So the rules say you do whatever is in the grouping symbol first. So inside our grouping symbol is 6 minus 8 minus 2, which would be minus 4. And the absolute value of minus 4 would be, anyone? Perhaps that folder will help you. Your folder's cold. Okay. The answer would be 4. All right. That one's probably more obvious because it was all inside the absolute value sign. Here, as I say, we treat it like a grouping symbol. So we do what's in there first. 6 times 3 minus 20, 18 minus 20. So we do that first. So then we're saying 7 minus that absolute value, and we get 5. Just like algebra, again with grouping symbols, this of course means 3 times the absolute value of minus 6, which would be 18. So they're all basic operations, which hopefully we're familiar with. So when we want to solve an equation or an inequation that involves absolute value, there are different ways of thinking about it. But if I have a question like this, absolute value equals 7, and I know it's a very simple question, and we should just go, bang, there's the answer for something like this. But I'm more interested in the thought process here. And it comes back to the original definition. And the original definition was that the absolute value of A could either be A or minus A. So when I have something like this, yes, the answer is x equals 7 or x equals minus 7. But what I'm really thinking is, okay, either x equals 7 or minus x equals 7. So even though I've written down the answer, x equals negative 7, that has come from the thought minus x equals 7. And you think, yeah, well, what's the point of that? When we start getting more involved, this 2x minus 3 equals 7. Then my thought process is either 2x minus 3 equals 7 or the minus of 2x minus 3 equals 7. And then I can solve each of those. And again, you might be thinking, well, that's no big deal because, I mean, you could have gone 2x minus 3 is minus 7 and got the same answer as well. Just write my final answer down there, minus 2 or 5. But, actually I'll do that example instead. But the reason I think about it this way is it solves a problem when it comes to inequations. I'll talk a little bit more about that when we do our first example of an inequation. Now, when you've got absolute value equals some piece of algebra, okay, you really need to check. So again, I'm saying either 2x plus 6 is 3x minus 1, or the negative of 2x plus 6 is 3x minus 1. The left-hand equation there gives me x equals 7. The right-hand equation gives me negative 1. But then we should always, as we do with any equation, but of course you don't because you're lazy and you've got used to just solving equations and accepting your answer to be correct, you should always be checking your answer. And you'll find if you sub in x equals negative 1, on the right-hand side of this equation, you'll get negative 3 minus 1, which is negative 4. And so you're saying the absolute value of something is negative 4, which of course is impossible. It has to be positive. So x equals negative 1 is not actually a solution. Why does this happen? The reason is, going from the first line to the second line, we have actually changed the question. What we're doing is we're saying, well, no, I'm not going to solve this equation. I'm going to create 2 new equations. Now, sometimes when you create new equations to solve a problem, the solutions aren't always true. Okay? So you should be checking your answers. This situation should only ever arise when you have absolute value equals and then just some algebra. If it equals a constant, it's never going to happen. So watch out for that. It is possible you could get an answer that's not a solution. So x equals 7 is the only possibility for this one. Okay. All right, back to our inequation. So let's say the thought process, if I stick with the same idea, I don't have to do anything new. I'm going to say either x plus 5 is less than 2 or the minus of x plus 5 is less than 2. If I had thought about it the other way, remember where we just said, oh, well, it's equal to plus or minus, the temptation would be to go x plus 5 is less than minus 2. But that would give us wrong answers. Because if you look at that closely, minus x plus 5 is less than 2 would actually be x plus 5 is greater than minus 2, not less than. So if we stick to thinking about it like the actual, what the definition is, like a could either be a or it could be negative a, then we shouldn't have a problem. So left-hand side, I get x is less than minus 3. The right-hand side, I end up with x is greater than minus 7. So my final solution, and often it helps to plot it on a number line just to see what's happening. So less than minus 3, but also greater than minus 7. So I must be in between these 2 points. So x is in between minus 7, minus 3. Let's just do another one. So either 3x plus 2 is greater than or equal to 1, or the negative of 3x plus 2 is greater than or equal to minus 1. So left-hand side, I get x is greater than or equal to minus a third. And the right-hand side, I get x is less than or equal to minus 1. If I put that on the number line, we actually don't have a point of intersection. So this must be an or case rather than an and case. So our solution is x is less than or equal to minus 1, or x is greater than or equal to minus a third. I suppose the other way you could do it is similar to what we did with quadratic inequalities and so on. Oh, sorry, inequations, I should say. Where once you've got your boundary points, you could just test values and see which region you're in. All right, let's have a look at absolute value graphs then. So what happens to our basic curve when we find the absolute value of it? So y equals the absolute value of function x. Well, whatever is below the x-axis can't exist anymore because we no longer will get a negative answer, but we'll get a positive instead. So it ends up reflecting above the x-axis. So whatever is below gets reflected above. If it's function absolute value x, this one's a little bit rarer, what would happen? Well, what that's now saying is I'm never going to substitute in a negative number because I'm substituting in the absolute value of x. So this time it's the y-axis. The left-hand side of the y-axis will disappear. And then the right-hand side would reflect over. So, look, here's y equals absolute value of x, and hopefully we recognise that anyway. But let's use this basic curve idea to get the absolute value of x. It comes from, there it is, y equals absolute value of x. But it comes from the line y equals x. So if I was to say the construction line was y equals x, and then I'm saying, oh, absolute value, whatever's below is reflected above. And we get that V shape. Or of course, I could think of it as the second situation too, because it's function absolute value x. Again, think of the line y equals x. Oh, left-hand side disappears. Whatever's on the right reflects over. When you're drawing these, it's usually good to plot a couple of points on there just to give it some sense of scale. So sometimes with the absolute value x, people put right angles in there. But that's only true, of course, if the slope happens to be 1. If it was 2x, there wouldn't be a right angle between them. So y equals the absolute value of x plus 2. We can now think of it as various ways. I can say, oh, well, it's the y equals absolute value of x curve, our basic one. Remember, absolute value is a grouping symbol, so it's grouped with the x. So therefore, I'm shifting it left 2 units. And that would be y equals the absolute value of x plus 2. Okay. That's one way I can think of it. I could think of it as, oh well, my basic curve is actually the line y equals x plus 2. But I'm going to reflect whatever's below in the x-axis. And I get the same shape. So it all depends on how you want to think about it. Absolute value of x plus 2. Okay, I can say, well, my basic curve is y equals absolute value of x. There it is. And this time it's not grouped with the x, so I'll shift it up 2. So there's absolute value of x plus 2. Or I could say the basic curve is y equals x plus 2, but now it's just the x value I'm absoluting. So the left-hand side will disappear, and the right-hand side will reflect over. Again, we get the same graph. Doesn't have to be a linear function. Y equals the absolute value of x squared minus 2. Okay, so I'm going to say my basic curve is x squared minus 2, so I've already shifted it down 2. Whatever's below, I'm going to reflect above, and I get this very interesting curve, like a W, I suppose. Now, if I want to solve an absolute value inequality, I could do that graphically. If I draw in the absolute value of x plus 5, and I draw in the line y equals 2, this is really saying, when is the absolute value curve below the line y equals 2? So if I can find those 2 points of intersection, so I could solve it like an equation and come up with the 2 values, and I'm saying, well, when is it below? For what x values is it below? Well, it's below between minus 7 and minus 3. I'm not suggesting that's a way I probably would go and solve it, but if you already had the graph drawn and they asked you that question, well, okay, it's probably going to be a quick way of doing it. All right, so a couple of exercises there to play with.